This is a Math 3 lesson summary video for the task titled Scott's March Madness. This is a develop understanding task. The purpose of this lesson is for students to be introduced to cubic functions and develop an understanding of how the degree of a polynomial function relates to the rate of change. Each year, Scott participates in the Macho March promotion. The goal of Macho March is to raise money for charity by finding sponsors to donate based on the number of push-ups completed within the month. Last year, Scott was proud of the money he raised, but was also determined to increase the number of push-ups he would complete this year. Below is the bar graph and table Scott used last year to keep track of the number of push-ups he completed each day, showing he completed 3 push-ups on day 1 and 5 push-ups for a combined total of 8 push-ups on day 2. Scott continued this pattern throughout the month. Here we have the diagram where n represents the number of day, and we need to find the explicit equation and the recursive equation first of just f of n, the push-ups each day. So let's start with the recursive equation. So remember, the recursive equation tells you how to get to the next term by using the term right before it. So we can look at our diagram and we can see that from one day to the next, we're just adding 2 push-ups. So each one of these squares represents 1 push-up, and to get from one column to the next, for one day to the next, we just add 2 push-ups. We could see it on the table also, where we're just adding plus 2 to get from one value to the next. So the recursive equation is going to be f of n equals f of n minus 1 plus 2, where f of 1 equals 3. Now let's look at the explicit equation. So the explicit equation relates the day number to the number of push-ups. So if we look at our diagram here, when n is equal to 1, I have 2 groups of the size n, so that's 2n, and then I have 1 extra. Let's see if this same pattern works from our other days. Now n is 2. I have 2 groups of n plus 1 extra push-up. For 3, I have 2 groups of n plus 1 extra. And then the same thing works for the 4th day. That means my explicit equation is f of n equals 2n plus 1. Now we want to get an explicit equation and a recursive equation for g of n, the total number of push-ups in the month. So to do this, I have my diagram and I've modeled each of the days to have the total. So on day 1 there was 3. On day 2 we had those 3 plus the next 5 to get 8. On day 3 I have the 3 plus the 5 plus the 7 to get the total of 15 for day 3. And so on. So to get a recursive equation, what we're doing each time that we're adding, we are adding this very last column here. And this very last column for this recursive equation is represented by 2n plus 1, the equation that we just found. So we have a linear change. The amount that we're adding each time is equivalent to this linear function. That means my recursive equation is going to be g of n equals g of n minus 1 plus 2n plus 1, where f of 1 is 3. All right, now let's take a look at the explicit equation. So remember that with the explicit equation, we are trying to relate the value of n to the value of g of n. So instead of looking at how we get from one term to the next, as we did with the recursive equation, we are relating n to g of n directly. So we know that this function, since it has a linear rate of change, as it's growing by this linear amount, we know that this function is quadratic, because quadratic functions have a linear rate of change. For quadratic functions, it's often easiest to get an equation, an explicit equation, by finding an area. And rectangles are really easy to find an area of. So for this, what I'm going to do is I'm just going to manipulate these blocks and see if I can make it into a rectangle. So for example, if I take this block and I just move it right here, then I have a rectangle. And the dimensions of this rectangle are 2 by 1, 2, 3, 4. All right, let's look at when n equals 3. For this one, I can take these 2 blocks and just move them into this space, which would create a rectangle that looks like this, where the dimensions are 3 by 5. Now for when n equals 4, if I take these 3 blocks and I move them over here, So they would stack up 1, 2, 3. And then I take this block and I move it right here. I can make a rectangle that has the dimensions 4 by 1, 2, 3, 4, 5, 6. Now that I've created these rectangles, I can more easily relate the value of n to the dimensions of my rectangle. So let me start with n equaling 1. So here, the width of this rectangle is the same as the value of n. And then the length of this rectangle, the height here, is n plus 2 more blocks. Let's see if the same pattern holds for the rest of my diagram. Here, the width is equal to n, and the length is n plus 2 because n was equal to 2. Here, when n is equal to 3, the width is n, and then I have n plus 2 for the length, and then the same thing here. The width is n, and then this is n plus 2. So my explicit equation, g of n, equals n times n plus 2. So to get the explicit equation, I knew I had a rectangle, and to figure out how many of these squares are within the rectangle, I just found the area, and the area is length times width. So I multiplied my dimensions to get an equation for the area. This year, Scott is doing even more push-ups. So he wants to do the same amount each day that he had for his total last year. So on day 1, he's doing 3 push-ups. On day 2, he's doing 8. On day 3, he's doing 15, and so on. Now what we need to do is get a model for the total push-ups completed for the month for this new year. What that means is we take the 3 plus the 8. So for day 2, for the month, he's doing a total of 11 push-ups. On day 3, we're taking this 11 plus 15, and we're having a total of 26 push-ups. And then 26 plus this 24 makes 50. And then on day 5, he'll have done a total of 85 push-ups. So this time, if we wanted to model this recursively, what we're doing is we're adding this quadratic change. So we have a new type of function that has a quadratic change. So let's write a recursive rule for this function. So with this function, to get to the next term, you take the previous term and then you add that quadratic value. So we have t of n equals t of n minus 1 plus n times the quantity n plus 2, where t of 1 equals 3. So this is a new type of function. It's called a cubic function. So let's look a little closer at our cubic function and find these first differences. So to get from 3 to 11, we had to add 8, and to get from 11 to 26, we had to add 15, and to 26 to 50, that was adding 24, and to get from 50 to 85, that was adding 35. This right here, we just looked very closely at this pattern, so we already know that this is a quadratic rate of change. Now let's look at the second differences of this cubic function. To get from 8 to 15, we have to add 7. To get from 15 to 24, adding 9. 24 to 35, we're adding 11. This is a linear rate of change. So the second difference for a cubic function is linear. Now let's take a look at this third difference. To get from 7 to 9, you have to add 2, and to get from 9 to 11, you have to add 2. So now we have that constant third difference. I want to move here real quick just to Desmos so you can take a look at this. These black dots are representing the cubic function that we're looking at, and these blue dots are representing that first difference, that quadratic function. So you can see here that the cubic function is actually growing faster. All right, just to summarize some of these characteristics of cubic functions. The first difference is quadratic, the second difference is linear, and the third difference is constant. It grows at a faster rate than a quadratic, but it's still not as fast as an exponential. Cubic functions model the sum of terms in a quadratic function, just like quadratic functions model the sum of terms in a linear function. There is also a relationship between the rate of change and the degree of the function. For a function with degree n, the nth difference is constant. Right? So for a linear function, there's a constant rate of change. Linear functions have a degree of 1, and the first difference is constant. For quadratic functions, they have linear rates of change. Here's their parent function, their degree is 2, and their second difference is constant. For cubic functions, they have a quadratic rate of change. Here's their parent function, they have a degree equal to 3, and their third difference is constant. Alright, that's it for this video. Thank you for watching.